I do want to talk about the subject of the video I asked you to watch. What is that video? What was it about? Sensitivity. What is sensitivity? Why do we use sensitivity analysis and modeling? Yes, Kate.
To see how uncertainty affects our models.
Good. Yes, in a word. To observe how uncertainty affects them. I could say, if I wanted to add, extra poignancy to it, to see the degree to which our results of our model are contingent on our assumptions, like about model parameters or about model structure. If what we get out of our model is just very wildly, given our range of uncertainty about a parameter, we assume one reasonable thing, it gives up a totally different in its results than if we assume another reasonable thing about that parameter value. We're sort of in a bad way, right? Because we sort of, and I'll come back to the sort of, because we've realized that, we want to be very cautious about counting on those model results, right? Can make two different reasonable assumptions and end up with very different consequences, very different implications. The reason I say sort of is that's one of the times it's most valuable to invest in data collection. To say, oh, okay, it's really sensitive to this parameter, to my assumptions about this parameter. That's a really good time to make the case that we really, really need to collect information, data, if at all possible, about that one. Because if we knew that value better, we could be a lot more confident about model results. Do you understand that point? See, a couple of heads nodding. Maybe I need to engage more vigorous recursive.
What are you gonna do one day if that payment breaks?
Believe me, I've been doing that for that people. That's like my favorite drum. Probably been doing that for 15 years for that people. Yeah, it's holding up pretty well. So when we're dealing with sensitivity analysis, we're asking how do model results vary with as we change our assumptions. Those assumptions can be about parameter values. What other type of sensitivity analysis is there? Yes. Structural, yes, and name again? Structural sensitivity analysis. What are we changing there?
The structure of the model.
Of the model, yeah. So it might be structured in the form of a state chart structure. Maybe we posit there's another state, of people who are infected but not yet infective. Suppose say latent infected state, or maybe we assume that there's people who are infective, can spread it, but who don't know they're infective, they're asymptomatic, so they spread it around. Various terms, oligosymptomatic and pouchy symptomatic, which are kind of less extreme forms of that assumption. But it could be a system dynamics model, right? Where we change the assumption about whether or not people can lose immunity over time, right? Got asked to do that early in the pandemic. We were simulating outbreaks in Saskatchewan's north, and one of the stakeholders there got a call at the office and said, no. Could you reevaluate these if you were to assume that immunity to COVID-19 is not lifelong, it's it fades. And we said, sure, what might be a reasonable fading time, a year or something? Turns out that was very prescient. This is like June 2020, May 2020. This is like 3 months out. And of course, it is, in fact, not lifelong, right? As we now know. Okay, so sensitivity analysis is about examining the consequences for model behavior as we alter our assumption. It could be about structure, it could be about parameters. it can be conducted in many different ways. And I've asked you to build, to open this model so we can have some hands-on components of this. Is that okay with you? Okay, I'm not seeing a revolt, so I'm going to begin to explore this. Okay. So the first thing I'm going to run is going to apply to some of the modeling types we use, but not others. And it's called a stochastic sensitivity. It doesn't involve changing any parameters. Doesn't involve causing change in structure. Instead, we're running the model over and over. What type of the three types of modeling types that we've been examining in this class, which specific type does that not make sense? It's just dynamics because it's deterministic, right? Stock flow models are deterministic. No? So the stochastic sensitivity analysis is commonly used for agent-based models. And it's commonly used for discrete events. Now, it's just gripping with things I know are going to be on the card all the time. Can anyone give me like that question? Can anyone say like within the past few lectures, have we seen an agent-based model that's deterministic? That's not his head. Could we? Any memory? That's the game of life. Game of life. Is that deterministic? All right, it is. Right. If I'm a cell, empty cell, I get colonized if I have exactly 3 gamers, right? If I'm a cell that's already occupied, I continue to live with my 2 or 3 neighbors, exactly. Totally deterministic. No stochastic. So I could ask them how to name. Protocol. All agent-based models are stochastic. And you would answer all, right? Okay, so I just ran a stochastic sensitivity analysis for this model, but really, I've done a terrible disservice. I mean, in fact, I violated the basic tenets of what I just invade upon you. I exhorted you and I abandoned them quite cruelly. To understand this behaviors, we want to understand the model gives rise to it, or have some hypothesis about that model. In this case, we can look at them. It gives rise to it. Okay, so there's a model you may or may not remember. I don't know how well you remember this model, but it has people situated in in neighborhoods and homes, and they can get sick over time. They can develop infection. And the infection is recovery from the infection is treatment mediated. What do I mean by that? Anyone? They can't recover without what? Thank you. I know I sound like a train, right? Treatment, without treatment. And in order to get treated, they have to present to a clinic, which is somewhere in there. I have a feeling it. Where's the clinic? There's a clinic that's probably somewhat hidden behind these folks right there. In any case, folks get ill. They can spread infection to others. Once they realize they're ill, they can, over time, have a certain propensity to go to the clinic. In which case they can get treated and attempt to just through that snuff out the infection in the population as a whole. And there are times where this infection dies out. But there are other times, you may recall, where it takes off. And do you remember this model? We used it to illustrate lock-in effects. Remember that? In this very classroom? Effects that, gosh, if you add 3 clinics from the start, the infection would never take off. But if you only have 1 clinic from the start, infection could get established so much you need like 6 clinics to clear it away. Do you remember that? Now, there was always a chance it would die out first, but absent that, there was a high risk it would spread enough that it could then go and reach very, very high levels. In this case, too, it died out. We're very lucky. But sometimes we will have it spread enough that it will reach very high levels, and we'll end up having massive levels of infection. So we have people, they can get infected, exposed to others infected, but in order to recover, they need to seek care. And then we have people who can seek care if they're in the infective state and transit to care. And then we have a clinic. And this clinic involves some healthcare workers treating the people, but if they wait too long, they leave. And otherwise, they go through treatment, and there's a chance they'll be successful or failure. It's a 5% chance, I think, of treatment failure based on this probability of success. And the probability of success is treatment 95%. And in which case they'll leave. They leave in either case, whether or not they don't know whether or not they're cured, but they go out, and if they're not cured, they can spread the infection more. You remember this one, basically? Okay, so we're going to be trying to understand the behavior of this from a sensitivity analysis perspective. We talked about it from a lock-in perspective earlier, and that's valuable. But first, we're going to look at the stochastic sensitivity analysis. So stochastic sensitivity analysis involves running a large number of runs, and it's called an ensemble of runs, a big collection of runs, which run it many, many times across my boards. And for each run, you get an average number of times that people have gotten infected. And on the upper one here, and an average number of times they've presented for care, they've gone for care. In the average clinic utilization associated with that. And so here we've run it many times in the baseline scenario. And you'll notice that the average presentation count is just over 2, the number of times they've gone for care. The average illness count is number of times people have gotten infected is just over 1.5. And clinic utilization is between 0 and 0.1 as the single most likely. So what this is telling us is there are a large number of runs where it doesn't take off. There are some where it does, and we can have 10 for example, infections per individual. So this is stochastic sensitivity analysis. We're running it again and again and seeing the results. By contrast, we can run the model as we vary a parameter. And typically, for each value of the parameter, you'll run it an ensemble of times. So here we are varying this parameter, which is contacts per day. And we're going to be, as we run it, we're going to be displaying the results here. There's average illness counts across different runs with different values of that parameter. And then we have an average number of presentations they have, and an average illness count here in black. Average presentations are there in green, a little bit further up, right? And this is average clinic utilization. So what is this telling us? If this is contacts per day, the x-axis for this graph and the scatter plot here, what is this telling me? What does it suggest? Is it sensitive? Yes. No.
It's saying like when there's very few contacts with the utilization. There's no utilization. Yeah, once it goes over the one, that means that it's essentially spreading. It's managing with that particular fact.
Right. Utilization is like what fraction of the time is the healthcare worker busy, right? This is up near one. What would you say? Why do you say it's up near one? Because what? There are lots of patients for them to treat, right? Okay, so now let's go up to this graph just above that.
Average presentation count and average illness count. So average presentation count, what is this saying? If this is number of times on average, someone is going in for seeking care in the population, and you have a scatter plot like this. Again, as the contact rate rises, you have this very low value, as 10 observed, to about 1, and then it goes very high. What is that saying about, like, what's going on? Can anyone tell the story about that? I'm not going to take 60 years about telling stories. Yeah, so I'm not.
Excellent. So what's going on here is speaking to my point earlier, my exhortation, nay, my rants, about thinking about these different types of data as not as solitudes, but connected, right? And Amna did a great job connecting. So average presentation count, what we see is that as the contact rate is low, we have few presentations going on, and the utilization is also small, because many people are coming in for care, right? As the contact rate rises, there's a fairly sharp transition to where we have very high numbers of presentations going on. You know, many people are seeking to present many times. And the utilization is correspondingly high. These two are not solitude. This is in some ways driving it, right? In some ways, people presenting for care is driving the utilization, right? I go to the clinic and therefore the nurse is busier. But is the nurse being busier, also driving presentations? How? Yes, it is. How? Excellent. Excellent. Yeah, and people won't get cured as quickly, and they'll spread it. In the meantime, we'll call you in 90 days. And meanwhile, they're spreading it. And that leads to more need for presentation. What's going on with illness counts here? Can anyone want to offer a mechanistic understanding of that? So these illness counts, what's going on down in this range? This is a bit easier. So again, this is contact rate on the x-axis, number of people per day they're contacting. What's going on in this range? Tell a story. Yes. Thinking mechanically is a lot of, it sounds like things, but it's not telling stories. It's about thinking what causes what causes what causes what. And stories took me like 45 years, 50 years to realize just how central storytelling is in convincing decision makers and speaking to people who have expert knowledge and so on. It's about storytelling. And it's not about storytelling that are arbitrary stories. It's about stories that hang together with our understanding of the world and with observation. So what's going on down here in terms of illness counts when our contact rate is low? Tell the story. Basic reproductive number is low, so the average illness count is low. What goes on over here? What goes on here? These are like 8 average illness count, 7, 8, 8.7, etc. What's going on here? Sorry?
Yeah, and that, they're, okay, so that's true, they're more than replacing themselves. And they're getting sick many times, right? Why isn't this just going up and up and up and up? I mean, after all, contact rate is rising, why is it going up and up and up and up? Why is it just plateauing? It's the story there,
Can't get better until you're treated.
can't get better until you treat it. So if you're not getting treatment, because utilization is too high, you're not getting called back by the clinic for 2,000 days or something, right? Or you just leave the clinic without being seen, right? You're not going to recover from that illness. So the number of times you get the illness is capped because at some point you're not going to get cured from it. And you're just going to carry it around all the time, right? And that, of course, is tied with this average presentation count. You may go back and back, but you're rebuffed every time you give up, right? Here's a histogram of the average illness count. Zero heavy, right? There's quite a few where it's zero, and then there's quite a few where it's much higher. Again, it's not arbitrarily high because if it gets high enough, they're not going to get treated and they just carry it. So the number of times they can get it in their lifetime is kind of limited by that utilization. But what are these ones in zero telling us? What's going on? What's the story? What's the story there? Why is it zero heavy? Why are there all these zero? Think about your data, think about what's giving rise to this, Malcolm.
Yes, in this sense, would there be a lot of cases where the virus never gets
Yes.
to take off because the
Exactly.
clinics don't ever come over well?
Exactly. Yeah, there are quite a few cases when we run it where it just by luck of the draw, by happenstance, it never gets fully established, right? And so it peters out in the population before it catches. And you end up getting very few homeless. Quite possible. Just like you try to start a fire on kindling and sometimes it doesn't catch, and you gotta try it. But if it does catch, you notice there's quite a gap here, right? If it does catch, you tend to have more, right? When it rains, it pours. If it doesn't catch, you have just about zero. If it does, you're gonna have lots, right? Kind of like that piece of glass in the, in the mountains of BC that is surrounded by dry tinder. Maybe in general, it won't catch, but if it does catch, there's a forest fire, a big forest fire that's going to occur. Right? So we see something along those lines. Now, there's other stories to be told here. For example, in the incubation period. The incubation period, just to remind you, is the time that they take to go from exposed to an infective state. So one of the best things, Malcolm asked, in his wise way, how can we learn to strengthen this sort of mechanistic thinking? One of the things you can do is ask yourself ahead of time, what do I expect? What do I think might happen? And then try running it and use it to debug your thinking, right? Use it to realize where your thinking is off base. If you don't think about it ahead of time, you just run it, you miss that big opportunity to realize, oh yeah, you didn't see that. You just look at it and say, oh, okay, that's interesting. It's really by sort of posing a problem and giving it a try, seeing in our mind what we think the result is, and then testing it. That's how we, Francis Bacon said, one sooner reaches truth via error than from confusion. There's actually some beautiful Latin, I'll note, Justin, behind this Francis Bacon quote, although it's probably getting close to enlightenment in Latin. And the point is, it's kind of the 16th century, version of fail early, fail often. Fail forward, right? Like, try something. Develop some idea, test it, and we learn something. If we just sit back and go, I don't know, we don't learn anything, or we shortchange our opportunity to learn. So, you could ask yourself, well, okay, as you change incubation period, as you change that period, that people go from exposed to infective, how do you think that will change things? What's the story here? Anyone? I'll run it because we're over time. What's the story here?
Typically, if they're incubating it longer, either they're contagious without realizing it early, so they might not see.
Okay, if the incubation, a great question. Incubation year is also latent period, so they're actually not infected. Well, so will it spread more if it's short or long? If it's really, really long, what will happen? Really, really long before they become infected. It will spread at least slowly, right? More slowly. If it's really short, it has at least the opportunity to spread quickly. And you'll notice if it's short, indeed, there can be many presentations for care. The average illness count tends to be above what it is, out here. Oh, well, actually, I'm not sure about that. This says 11. This says 4. Okay, actually, I stand corrected. Okay, I'm debugging my thinking. Presentation count is hard because they realize they're infective and they go in for care sooner. The average illness count, well, there's a more textured story, it looks like. It's actually somewhat higher out here. We still have 0 heavy. Clinic utilization, why is it lower if it's really long? They're not going to hit the clinic for longer, right? Like, they're not going to realize they're infected for longer, so that it's going to be a while till they go in for the clinic. And comparatively speaking, the fraction of their entire illness that they spend infective is going to be, well, they need to go to the clinic to get recovered. But you'll notice the clinic utilization is actually rather higher if they have a short incubation period. It's a short time for them to start getting infected. This is something which requires some thinking to tease through, and we'll talk about it a little bit more next time. I will say that also in this model, you'll find multi-way sensitivity analysis that examines both those parameters, as well as a Monte Carlo that flips coins for what the value of the parameter is. Okay. Hopefully that's a useful lesson. Useful lesson for some general principles. We'll see you on Thursday, and thank you again for your efforts. Sometimes heroic to get in here despite all the obstacles. I really appreciate it. Take care there.